In this video demonstration, we're going to talk about stiffness modifiers and how they can be applied for the design of transfer beams or for the evaluation of transfer beams. We'll also talk about crack deflections and how we can check crack deflections for transfer beams with the consideration of the applied loads that are bearing at the beam. And we're going to go ahead and use Builder 2019 beta for this video. This is similar in process to Builder 2018, so there's no real change in how both versions of the program consider this. We're going to go ahead and just launch Builder. We're going to create a simple model. This is going to be an RC transfer beam, so the same method would be applied both to PT or to RC. We want to have Edge and Floor Pro turned on. We'll be working in US unit system today, and I'm going to first go ahead and create some different floors to this model. I'll add just a few planes, and then I'm going to modify the planes just for consistency here. Okay. Our transfer beams we're going to say are going to be at plane 3. So let's lay out a grid. This will be a pretty simple example, but it should be applicable to more complicated models that have similar conditions and just the need for these types of checks. So I'm going to use the grid settings and set up a column grid. Go to model, and I'm going to model some 24 by 24 inch columns. We're going to have a 30 foot, a 40 foot, and a 30 foot, and I'll just go ahead and repeat that pattern. And we're going to repeat it every 30 feet in this direction. We'll just do 4 bays. In those bays, I'm going to model a transfer beam. So the transfer beam is going to be, let's say 22 by 34 inches. Okay, and then I'm going to change the grid to 5 by 5, and we're going to go ahead and model just a slab on top of that grid. This is by default an 8-inch slab. Okay, and again, this is all occurring at plane 3. So if we go to a side view, we have something that looks like this. If I go to multi-story, I'm going to take these columns and actually just copy them down so we can see them copied in multi-story. So we'll go back to modify vertical, and I'll copy these down one time. Okay, and we're going to also copy this slab down. It'll just be a two-way slab at the level below. I can go back to single level, navigate to the second floor. Notice there are no beams here, but I might want to introduce just additional columns since we have those beams are not included. We'll put another row of columns there, and coming back up to level 3, we're going to now have a change in the geometry, moving from level 3 to level 4, and then at all levels above that. So if I go to multi-floor mode and then I switch the active plane to plane 4, that means I can still reference in view what's happening at the transfer level, but I'm modeling everything relative to plane 4. So what we'll do is we're going to have basically 2 lines of transfer columns. These columns right here are going to be copied vertically, so we're not going to worry yet about those. Let me turn the grid back on, and I'm actually going to create a column line here and also a column line here. So there's two transfer columns on these beams. Okay, if we look at this at level 4 now, we'll go to single level mode. We've added these columns. If I go back down to this level, I'm actually going to copy these columns up multiple times. So let me select those columns, and I'll switch this to a 3D view so we can see what we're doing here. So I'll take these columns and modify, copy those vertical. I'll copy those up 5 times to the additional floors above. And then I'm also going to take these columns that are the transfers. I'll copy those. I could have selected those also with these outer columns. We'll do that 5 times. It's really only copying it to the floors we've established. And then finally, if I go up to level 4, let me switch back and toggle to level 4. We're going to create 2 slabs. Okay, so we'll model a slab region. So the building basically splits at the level 4 and above. There's slab region 1 and slab region 2. And you'll notice these are pretty, this is a 30, let's see, 10, 20, 30 foot span there. So that's fine. So ultimately our final product looks something like, make sure I am viewing everything. It will look something like this. I need to actually copy these up now 5 times also, or 4 times. So modify, copy the slabs up 4 times. Okay, and we'll save this. If I go to visibility and just show a rendering of this model, this is what it looks like. Our ultimate goal is to be able to evaluate the deflections at this level with cracking and or with stiffness modifiers. Not only the deflection, but we may want to design this level based on the level of cracking that's happening in those beams. All right, so we're now going to load the beams. I'm going to select by type all of my slabs. We'll just add some gravity load here to the model. I can use Patch Load Wizard to map load to the slabs, and we'll add dead and live load. We'll use let's use 75. Okay, so we add load. Now there's 2 ways to obtain a design of this beam in terms of the loading. We can use what's called load takedown, and the load takedown means we're just compiling the geometric tributaries of the columns and stacking it on that beam. Or we could run this for finite elements or with finite elements and obtain the reactions and do the same thing. So the first thing we're going to do is run our tributary load takedown. We're going to demonstrate the use of just stiffness modifiers to evaluate the transfer beams first. So I'll go to this option for load takedown. I'm going to generate the tributaries, calculate my loads, and the program ultimately gives me loads in these columns brought down to these transfer beams. That's all separated. It's independent of running this in finite elements. And if you go to the analysis tab under load takedown, we can actually see the tributary boundaries. So if I start at the very top of the structure and I turn on the cumulative loads, the program will isolate and show us the load buildup in each one of these columns. So these inner columns on the split slabs above are what will be transferring load out to these beams. So when I go from this level 4, this set of loads, 48, 180, 263, that actually gets split, and it will end up, ultimately it will end up down in these columns. But we want to evaluate this beam, these beams in this level. So this just gives us the ability to then use those reactions in these columns when we analyze this one floor in isolation. Okay, so that's the tributary takedown. You can look at the transfer path for the loads. This is showing us how the loads are being transferred for these particular regions. This particular column transfers 75% of its load to this column, 25% to this column. If I look at this one, this also will transfer, load to a given set of columns. And what we're going to do now, we're going to run this level in isolation. Okay, by default, there's a usage case. Under Stiffness Modifier, there's an uncracked usage case. So if we analyze this level with tributary reactions, the program will solve for this level, for the applied loads at the level plus the reactions in the columns. And it will assume basically an uncracked state unless we tell it not to. And we're going to tell it not to by editing the usage. And I'm going to say this is going to be cracked. Let's call it beam crack. Okay, now I'm going to select these beams. And in this case, we don't know to what extent the beams have actually cracked. We're just applying a modifier that is approximate. Maybe the ACI code or another code says for second order effects, for strength, for this, for that, we apply certain modifiers. So we'll apply a modifier of 0.35 to this beam for flexure, just as the example. After I set up the usage case, I'll select the beams, I'll use modify selection, and for beam we're going to go to stiffness and we're going to change this to 0.35. Okay, and that changes those modifiers. If I go back to one of these beams and I look at the modifier, you can see it's set to 0.35 for M11. M33 still was at 1.0. Let's make sure that that gets changed also. So let's come back here. Okay. Now I'm going to run this level. I'm going to first, I have to mesh it now because now I have to run finite elements for this level and resolve it with the reactions. So I'll go ahead and mesh this. I'll mesh it at 5 feet. And we'll execute the analysis. Here we just have some basic gravity level service and strength combinations. The most important thing here is to note we're going to include the load takedown. This applies those reactions that were saved from the tributary run, and you can see for dead load the solution source is tributary. There's also an envelope, but we haven't run any of the global finite element runs yet, so really the envelope is just tributary. So there's reactions for dead, live, and self-weight. I can now run this as uncracked or beam crack. So we're going to run it assuming the loss of 65% stiffness for the beams. Once I run this analysis, I can then, I can check deflections. If I look at the beam deformation here in the Z direction, this is the beam element deformation under that cracked condition, under that cracked state. I can look at slab deformation on top of beam deformation. The slab is not cracked technically because we didn't assign a modifier to the slab. We only assigned it to the beam. In reality, you would likely assign it also to the slab. So, and you could assign it to the same usage case. I could come into the slab and put a modifier for that same beam crack right here. We just didn't do that in this case. So we can check deflections. These are immediate elastic deflections based on the service total and service sustain case. These are not cracked deflections that the program has checked. So in this case, we artificially crack it by applying the modifier, check the deflection. This also does not include long-term. We would have to use some multipliers potentially to predict the long-term under a artificially cracked state. Um, and again, these results are based on tributary load takedown reactions in the columns on the transfer beams. We can also design the beams based on this particular run. So if I, for example, create a support line on these beams, let's do that. We'll go to Y direction support line. And I'm using, again, version 19 here. One nice thing about 19 is you don't have to use any splitters to obtain the proper geometry for the tributaries. If I generate the sections, you can see the program creates my design cuts. I could also set these, if I set these to design as a beam, which is required if we want to design them as a beam, you can also now include the option to have the program use the effective flange width when we design the beam. The program will still solve the actions at the beam based on this integrated cut line, but it's limiting the actual properties of the beam to the effective flange. So that's available as well when you designate this as a beam. So once I set these up as beams, I'm going to now design the sections. This design is all based on the underlying assumption of running it with these cracking modifiers. Okay, so when I design this and I go back to my design sections now, I look at my actions. These bending moments for which the beams are being designed for are based on cracking at 65% crack, or 0.35 IG in other words. Okay, and we could now calculate rebar based on this assumption. The alternate way of doing this would be to obtain finite element reactions. So I'm going to back up and now go to multi-level mode, and I'm going to mesh the entire model because we want to obtain reactions in those columns, but we want to base the reaction now on finite elements. So we're going to execute the analysis for finite elements. Notice that this actually is inactive. This is grayed out. It doesn't apply to global run. And I'm not going to use beam crack here. I'm going to actually analyze this as uncracked, just for the purpose of comparing it with the tributary result. The only time I'm setting that usage case to beam cracked is when I rerun in single level mode. If I did run this as beam cracked, that's okay. That just means the global solution would assume 0.35 IG when it writes these elements into a stiffness matrix. So you crack those elements for the global solution. Okay, so that's fine. You could do that also. Now ultimately, if I'm running a full global solution, we're likely going to have other elements that are cracked to some level if we're applying modifiers. So here we're only cracking the beams for the sake of the example. I run a solution. I have two options. I can design the beams based on a direct global solution. So I could immediately go to plane 3. We already have the design strips. I could design these section cuts. This means that the beams are now being designed for uncracked IG equals 1, or 1 times IG, and it's based on a global run, not a single level run. So once I do this, I can again obtain diagrams for bending, shear, axial, whatever the diagram is, and I can again directly go in and generate rebar. In reality, these beams are likely going to be cracked. So this is really not a true workflow because the entire model was assumed uncracked, let's say for strength level design. The other option from the global solution is to rerun this. I can now rerun single level under analysis with beam crack, but rather than using the tributary, I'm going to use the uncracked solution from global. Remember, I ran global analysis with the uncracked usage. I'm rerunning the single level as if the beams are cracked, but I'm using the global reaction versus the tributary reaction. Okay, and we'll rerun this. And this is our third workflow for obtaining a beam design with use of modifiers. And we're going to go back to floor design and design the beams. If I display the section cuts, we again have some solution here. I'm not really comparing solutions, just defining the workflows. And again, we can calculate reinforcement in the beams.